right. Hi, everyone. So a warm welcome to our workshop working with the RDKit in KNIME. It's 6 o'clock. I would maybe already go ahead and do a bit of the housekeeping to maybe wait for while people are joining. First, something about myself. I'm Alice. I'm one of the life science data scientists and life science team, and I have Greg Landrum with me, who's a chemical expert and one of the heads or the head behind the RDKit.
Hello.
And so, yeah, as I said, something about the housekeeping. So you guys are following that via the event Mobi. There are two sections. There's a section for the chat where you can go and just post where you're from or connect to other participants. And there's a section for the Q&A. So if you have any questions about what we're presenting there and some chemical questions, workflow questions, go ahead, please, and post them in the Q&A. We will monitor that and then pick it up live. So something about the agenda today. I will go ahead and give a brief introduction to KNIME, and then also in the first part tell you something about reactions in RDKit and how to do that. And then in the second part, Greg is going to show you a really cool 3D visualization of molecules that I'm also going to look forward to. Just as a bit of a disclaimer, this is called a workshop, but we decided to keep this really like non-interactive in the sense of that you guys are not given any time hands-on. You are provided with the workflows, so you can go and download them and play around with them on your own at your own speed. If you still have questions, then afterwards, when you really get touch on it in the KNIME Analytics platform, you can go to our forum, to the Cheminformatics section, and post a question there, and then we will go and pick that up from there. So the workflows, we're a bit last minute. You didn't get them beforehand, but I think Greg will post them in the chat right now. So they are already on the KNIME Hub. And from there, I would go and ask you to click the whole or download the whole workflow group. So by that, you have both of these workflows already downloaded in an R file. Once you have downloaded then the NAR file or the workflows, you can just go ahead and double click, and then this window will pop up. Where it's gonna ask you where to put the workflows within your KNIME Analytics platform. So I now installed it in my local workspace. And then the two workflows show up here in the KNIME Analytics platform, upper left corner. And you can go ahead from there. If you haven't been doing a lot of chemistry in KNIME before, you might need to install some extensions, some special extensions to deal with chemicals. And the easy way is just to go and open the workflows. And then these pop-up windows will come up, where you will just get asked if you want to install the extensions, and then you can go and gonna get rid of the touchpad now and do it with the mouse. And you can go and click yes, and then it will ask you to restart. And if you want to take the more complicated way, you can also go via File, Install KNIME Extensions, and then select manually all the extensions you want to install. So for these two workflows today, we would need the ChemAxon extension, of course, the RDKit, the KNIME-based chemistry, and the Vernalis nodes. So coming to the introduction to KNIME, you're here at the KNIME Summit, so I assume you all know the basics. For the ones who don't, I'm just going to quickly cover some really just the basics. So what is the KNIME Analytics Platform? The KNIME Analytics Platform is a tool to analyze your data, to manipulate your data, to really crunch it, and also do visualizations and reporting just straight out of there. It's based on the graphical program paradigm. So that means you don't have to code if you don't want to. And it comes along with a diverse array of extensions. So if you just go and download the KNIME Analytics platform, it has some core functionalities, but if you want to have some special functionalities, like today with this chemistry, you need to install these extensions. And so we have some, as I said, some Cheminformatics extensions, but we could also go and get some extensions for text mining and network mining. And also especially for us life scientists there, I would want to point out a really cool use case where we use this text mining and network mining to analyze a patent. And as I said, if you want to code, you can still go and use your chunks of code, Python, Java, R, whatever, and also go and get that integrated in KNIME. So as I said, we're not having any code, we're just having these little colorful boxes, which are the nodes. And these are then going to the, we can just go and drag and drop them and build your workflows there. Something about the KNIME ecosystem. So there are two big chunks. So on the left side, we're having the KNIME Analytics platform. This is the open free software that everybody can go and download. We have a lot of extensions that are free as well. So and also the KNIME integrations from either within KNIME or some extensions coming from either the community or certified partners. So this all runs on your local machine. And if you want to go ahead then and do more of a collaboration or really go big, we have our commercial product. This is the KNIME server. So from there you could go and deploy your things. You have something like automation. You could terminate, like say when a special workflow should run, or you could also go and have data science as a service. So you can let the web portal run over like from your workflow and offer that to users in a browser so that they would never even have to touch a KNIME workflow. But today we're just going to focus on the left side. So everything we do today is free and open. So this is then how the KNIME Analytics platform looks like. I assume most of you guys know that. So you have in the middle the workflow editor. This is where you drag and drop your nodes and you build the workflow. Then in the upper left you have the KNIME Explorer. This is where the workflows are and the workflow groups, so the folders, and where you can also have mount points to the server, and there's always by default a mount point to the hub. Then in the bottom left we have the node repository. This is where you get your nodes and you can go and drag and drop them to the workflow editor. Then something optional is the workflow coach and the outline, so just showing me the whole workflow. And then something really useful if you're not really sure about a node, for example, what is the input, what is the output, what are the configuration windows, is the description that's always on the right side. So you can always click a node and then get either a description and more information about the single node or about the whole workflow. So I said we're having a node for each task you want to do to the data, and we're having a lot of nodes. So I'm still having 3,000 plus here, but we're almost at 4,000 nodes for all kinds of tasks. So we have nodes for data access. This is just so it can be for single files, Excel files, TSV, CSV, text, whatever you're having. We're also having a lot of connectors to databases, SQL ones, non-SQL, for example, MongoDB. We're having a lot of nodes, of course, for transformation. So whatever you want to do to your data there. Nodes for analyzing and data mining. So this is where all the machine learning nodes would go in. Of course, nodes for visualization, where you could go and check some results of your data, and then also eventually some nodes to write out whatever you created. So either models, like here, for example, or the data itself. And we also have nodes to include the results and reports. So almost 4,000 nodes, that's a lot. Don't worry, you don't have to know all of them. We do neither. So we have a really great place where to look all that up and where to find what a single node does or what nodes there are in the first place. And this is the KNIME Hub. So whenever you want to have some more information or you find a node and see how it works in a workflow, how to configure it, what is the input, what is the output, have example workflows. The hub is really a great place to go and see how other people have used that node. You can also go and look for components there. So as you see there, you have components, the single nodes, and also workflows. And you can also get more information about all the extensions. As I said, if we have some hardcore scripting guys, really convinced scripting guys amongst you, we are also having nodes for R and Python integrations. So a lot of different nodes for different tasks. They work with all existing Python and R installations. And when you include your code here, we even have some syntax highlighting, which makes it much nicer to go and code in there. Of course, we're going to go and focus on Cheminformatics today. So I would want to point out some open source extensions for that. You already saw some of them that we're going to use today. So of course, we're going to use the RDKit. But we're also having the CDK extension and the Earlwood nodes. They're also for free. So these are maintained by Eli Lilly. And today we're also going to go and use some Vernalis nodes. In case you are either a commercial user or a pharma company, or your university has some licenses for one of these companies, you can also go ahead and check out these. So these are Cheminformatics extensions that need a license. And we're having nodes for SolveIT, some Chemaxo nodes, Cresset, CCG, and Schrödinger. But we're not going to use them today. And one of our beloved extensions that we are mostly using here at KNIME is, of course, the RDKit. So what is the RDKit? That's an open source Cheminformatics library that has been written in C++. And there have been wrappers in KNIME, which are maintained by the open source community. And there's a lot of functionality that you can do within these nodes. So you can calculate descriptors, what we're going to do today, cleaning structures, ING conversions, canonicalizing smiles, what we're also going to do today, fingerprints, scaffolds, and the reactions, and many more, of course. And with that, I'm already at the end of the introduction and would go ahead to my first part. So first, some overview. So this is the workflow I'm going to show you later in detail. And what we're going to do there is that we are reading in a set of compounds. I think it's 53 or something. And then we want to do a reverse reaction first, like a reverse reaction. So we're just going to take first these molecules and go from there and take the 2 blocks, like do a reverse reaction to get to 2 blocks that these molecules are built from. And then in a second step, go to the 2 component reactions, where we then take these individual blocks of the molecules and go and have them all with each other react again. And then in a third step, go ahead and see which of the molecules that we created were already in the initial data set. And then of course also going to have some basic visualization at the end. Just some background about the data. So they were taken from this paper. This is also open source, so you can also go and download the CSV file so it is within the workflow, but in case you want to go and have a look separately. And they had this tetrahydroindazole compound here, and they optimized it, and then in the end came up with these 50-something analogs that are the initial molecules that we're going to start from. Just going into some notes here that are, I think, are worth covering, except from with outside the workflow. So the first one is, of course, the file reader. So we first have to go and get our data into KNIME. So this is how it would look like then. This is the file reader node. If I double click and configure it, I can here go and direct to where this CSV file is that I want to read in. And this is how the data would look like. So we're having the molecules and some other data along. And pro tip here, if you have been in one of our courses, I'm pretty sure you've heard that before. If you go and want to share this workflow, use the workflow relative path to point to the data. So of course I can go ahead and just click here browse and then do all the local path and direct from there to the file. So for me it would be C, users, Alice, whatever. But if I then want to go ahead and share this workflow with Greg, that's not working that well, because of course for Greg this local path is something completely different. But if you use one of the workflow relative paths, like here, this KNIME /KNIME.workflow, this data is already in there and pointed at, and Greg can just go ahead and open the workflow and will find the data directly. Then a second very important note today is the Marvin Sketch. So this is where we're going to come in and draw or give the template for the reaction that we want to do. So in the screenshot, this is the input for the 1 component reaction. So these are our initial molecules that we just go and separate them. And you also see these numbers there. So I can see that the molecules have been mapped. And there are 2 ways to do that. So either you go and to this arrow and click it and do that all manually. Or you can also go ahead and click on structure and then mapping and then map atoms, and then the Marvin Sketch will do that all automatically for you.
At least it's worth mentioning at this point that if you're a chemist, you may not be used to mapping reactions because it seems kind of silly to do. But because the computer is stupid, the reaction nodes can't do anything with reactions unless you have mapped them.
Right.
So if you don't do that atom mapping step that Elise just showed you how to do, the RDKit reaction nodes will not know what to do with the reaction.
Right. Yeah, Then coming to the first RDKit reaction node. So this is the one component reaction where we are just taking this one reactant molecule. This is where we're giving it the reaction that should be done on these molecules. You can go and randomize it, but we're not going to do it. And this is in the end how it's going to look like then. So we're having here the input molecules, and this is the two blocks that are coming then out of the, are going to result from the reverse reaction. The second reaction node that we're going to use is the RDKit Two Component reaction node. So this time we're not just going to have one starting molecule, but we're going to let two molecules react with each other. So these you go and configure here then. So this is where I'm going to tell it which are the molecules. And again, here I'm giving it, in this case, an RxN reaction. Again, I can go and choose to randomize it. We're not going to do it. And down here, you can click the Do Matrix Expansion. This is important, so we're going to do this today. If you're not clicking that, it will just go and take one block and react it to exactly this other one, but it's not going to go and let it react with all the other blocks. And this is how the output would look then. So we're having here the reactant 2, and this is getting indexed. So because we're in computer science, they all start with 0 and not with 1. So, and these are then gonna react with this reactant, and this you can see here on the sequence index that this is all the same molecules still, and this is the resulting product then. And from there, I would also go and change to the KNIME Analytics platform now. So this is how the workflow looks like. As I said, we're going and reading the data here. So we can see they're having some other information from some assays in the data set. And we're mostly interested here in these molecules. And the first thing I do then is, because these are still in smiles, is that I use an RDKit from molecule node to bring it into an RDKit format. Then I go and canonicalize these smiles. And then I have my first reverse reaction. So down here, we're having this Marvin Sketch that I just told you about. So this is where we're telling the computer what reaction it should actually go and do to the molecule. And this is then fed in here in this special port. So here's where the data is coming in. This is where we're going to tell the node which reaction it should do. And this is how the output then looks like. So we're having here the reactant that's going in. This number is the line number in the input data set. And here we're having this product index. So you can always see that this is 2 times 24. So this is the molecule that was in line 24 in the input data. And from there, we're having these two products, product index 0 and products index 1. And this is what's happening for all of the molecules. From there, I would go and use the row splitter. So this index column is what I'm using as an input for the row splitter to split these products to amines and to acids. So if you look up here, this now all with the product index 0. So these are all the amines. And down here we have the acids. And I also go and look for duplicates there. So this is where we're having all the assets. You can see that there's always the one here. And this is then what I use for my two-component reaction. So you can see that this time we're having two input ports. So in the one I'm feeding the amines, and in the second one the acids. And down here I'm having another Marvin Sketch, where this time I'm actually telling the computer what reaction it should do to, like, the merging reaction, combining reaction it should do to the molecule. If you don't want to use the Marvin Sketch and you feel more comfortable doing that with smiles, you can also do that as a flow variable. So by default, or not by default, but in the first tab, you can see that it's asking for a reaction column. If this is not suitable for you, you can also go and in the flow variables tab, go and feed it some reaction smarts as a flow variable. So what's coming out of there is not a question.
Yes, there's a question that's come up. So the question is, if there is more than one way to match a reaction substructure to a reactant, will the product be the result of all of the possible matches, or can it include all matches? And I'll go ahead and answer that because I happen to know. If you have multiple matches of a reactant onto one of the reactants of the reaction, you will get multiple products. So you'll get multiple output rows. So for example, if you have a two-fold symmetry so that you can substructure match on twice, you'll get two different output rows. And yeah, I think that's it for the questions for the moment. There's some other ones that I'll answer online.
Okay. Yeah, I think this is what I wanted to say there. So we have now the product. So we're having these two blocks from all the input molecules and let them all react with each other. Again, I was mentioning, if you're not clicking the matrix expansion here, what will happen is that it's just taking block part 1 and let it react with this other part 1, but not with all the other parts. So in the end, I mean, now you can see that we're ending up with, I think, 340 molecules. If you go and do that differently, you're ending up with much less molecules, just 18. And this is because we're having, I think, 17 molecules up here and 19 down here. So you can see it's not really getting the matrix, but this is what we want to do. So I'm just going to go and change that back again. So yeah, from there, I'm gonna go and canonicalize my reaction products. I'm also doing some duplicate row filters. So I'm pretty sure that there were some molecules built twice, so I can go and check. Right here, we're having 340 molecules. After the duplicate row filter, we're just having 165 left. And then I also want to go and see which of my reaction products is already in the initial data set. And this I'm doing with the reference row splitter. So I'm giving it two different input tables here. So this is now where I get the input from my reaction. And if you see that, this is where I'm going all back and get the molecules from my initial data set. And then I just want to have an additional column where I see if this specific molecule has been in my initial data set, yes or no. And I'm doing this with the constant value column. So here I say I want to have a column initial molecule. If it has been in there, I say If it has been in the initial data set, I say true. If it has not, I say false. And I can see that. So this is coming from the reference row splitter. If you see it here, the upper port is the table comprising the reference rows, so the molecules that have been in the initial data set, and the lower port would be the one comprising all the other rows. And this is then how my initial data or my final data set looks like. I have all the products and the blocks that they were built from, and in the end also a column on the very right side that says if it has been in my initial data set, yes or no. And then just something, a very basic visualization at the end. So from there I go and do some, I calculate some of the descriptors. We have a question.
Yep, before we move completely off the reactions, there's a question that came up that I can also answer because it's a detailed question. The questioner asks, if you define variable R groups in Marvin Sketch, will the RDKit reaction node recognize the reactants? And the answer is no. So you need to provide the reactants in a separate table. It does not work with the R group scheme where you draw a molecule with R groups indicated, and then you have the R groups, the identity of the possible R groups elsewhere in the same file. The RDKit does not currently support that. So you have to draw a reaction that shows how to attach the reactants to each other to make the output molecules, and then you provide those reactions in input tables.
More questions?
No, I think that's it for the moment. There's a couple that we can pick up later.
All right, then I would just go ahead and first finish my part of the demo. So at the end, you can see I'm having a component for the visualization. I'm not going to go into detail here. I think Rich is not having the time about these components. But you see our favorite plot, the parallel coordinates plot. So each line is one of the molecules, and here I have each column is one of the descriptors that I calculated. Now, just quickly something I want to show. So you can go and drag around these columns like you want, and then something that is not super exciting as a finding, but still interesting. So this is my average molecular weight. And here I got the number of heavy atoms, and you can see that most of the time the lines are quite horizontal, but there are some where the molecular weight is quite high, but the number of heavy atoms is actually quite low, so where the line would go down. And because this is a really nice interactive view, I can just go and select something. So now I tried and to select all the lines that go down, and then have a look down here in the tile view what the molecules actually look like. And as expected, you can see the high molecular weight comes from some halogens that are in the molecules. So I can see all the molecules got a bromide in there. And this would be it for my part of the demonstration. Going back to the slides, and would hand it over to Greg for the 3D visualization.
Thank you, Elise. Can you go to the next slide, please?
Yep.
So I'm just going to briefly describe the use case that I'm doing, and then I'll skip straight to KNIME. So what we're doing here is to build a browser for the most recent protein ligand crystal structures from the PDB. And so what the workflow is going to do is download the most recent structures from the PDB, the most recent X-ray structures. download the 3D structure of the ligands that are present in that protein crystal structure, and then provide an interactive view allowing you to browse through the ligands and the proteins and visualize those in 3D. So that's the high-level overview of what we're doing. There's the picture of the workflow. Let me share my screen and we will take a look at the workflow itself. So here's KNIME, and I have the workflow open. Before I start, if you've downloaded this workflow, I think you will see the note here. This is an important disclaimer. The PDB web services that we're using in this workflow are going to change in the beginning of December. And when they do that, the workflow, this particular workflow will break. It just won't work anymore. There are a new set of Vernalis nodes that will be available by that point that we can then use to continue to work with the new web services. But we will update the workflow in the same place that you just downloaded it from and remove the note. So if you are using the workflow and after at some point in the beginning of December it stops working, it's because of this web service change. And what you can just do is come back to the link where you got this one, download the new version. Hopefully this note will be done. It'll cause you to update the Vernalis nodes, and then you'll be able to work with the new PDB services. So I apologize, it's a little bit awkward for me to be doing this demo at this point, but I like the workflow a lot. I think it's really useful and I'm really super happy with it. So I decided to go with it anyway. So what we're doing, let's go through the steps of this. So the first thing is to get the most recently published PDB entries. And for all of the interactions with the PDB, or at least the first 3 important ones, I'm using the nodes from Vernalis. So these are some nodes written by Steve Ruffley. These are really fantastically useful for working with the PDB. The Vernalis nodes have a bunch of other useful stuff in it. I'm just going to use the PDB ones here. So when I configure the query node, it has a lot of tabs that allow me to get very detailed control over the query that's being made to the PDB. I've only changed a couple of these tabs for this use case. So the first one is on the deposition tab. I have said that I want to retrieve only the latest release structures. So I'm not interested in retrieving the entire PDB, that would take forever. And I'm also not interested in retrieving structures from a year ago. The purpose of this particular workflow really is just to get the most recent structures. The other thing I'm interested in is just to show some of the additional capabilities of the node. In this case, I'm only going to download structures that have experimental structures that have an X-ray, that are generated with X-rays, sorry. So we're not going to get NMR structures, and we're not going to get electron diffraction structures or any of the other types that are in the PDB. We're just getting X-ray structures. And that's it. Otherwise, the rest of these nodes the rest of these tabs I haven't changed anything for. When I execute this, it goes off and queries the PDB. I'm not going to do the queries here because it takes a minute or two to run and I want to just get through the workflow. And the output of this node is quite simple. It's just a table that contains a list of the PDB IDs. So you can see here, I got 294 PDB IDs when I ran it. If I run this tomorrow, assuming that new structures have been released, I'll get different results. Right? So this is really, it's always going to get the most recent data when I run it. The next thing I want to do is for each of those PDBs, each of those PDB IDs, I want to get some information from PDB about what's present in that crystal structure. And for that, I'm going to use this connector, the custom report. The thing I need to tell it is what the PDB ID column is. So that's PDB ID. And then I need to tell it which report I want because there's a number of different reports possible. I'm interested in the ligands, so I just pick a predefined ligand report. I can also customize the report if I want to, but this custom report returns all of the information that I want. So I'll just pick the custom ligands report. You can see that there's a number of other report types available that Steve put together. So I'll just take the ligand report. What comes out of that is a table that has a little bit more information in it. So now I have 9 columns. I still have the original PDB ID. Now, because the ligands can be associated with different chains in each structure, I also have a chain ID. If there is a ligand present, I have the ligand ID. So let me find one where there is a ligand present. Okay, so if there's a ligand present, I have the ligand ID, and then I have some information about the ligand that the PDB has provided, as well as the smiles for it. You can see I now also have more rows in the table than I started with. So I had 294 structures, and now I have 1,510 rows. And that's because an individual PDB ID can have multiple ligands in it. And in this case, as you can see, it's not always what I, as a chemist, would think of as a ligand. Like zinc isn't really a ligand as I'm thinking about it. But we'll see later about how to get rid of the irrelevant bits or these smaller pieces. Okay. The next thing I do want to do is get down, because I can have multiple ligands per structure, next thing I want to do is get down to have only the largest ligand for each structure. So I have a table that has has the PDB ID present multiple times, so multiple rows per PDB ID, and each of those has a different ligand. And what I want is for each PDB ID, the ligand that has the largest molecular weight. Back up until a couple of KNIME releases ago, this was a little bit tricky to do. You had to use a couple of different nodes in a loop, but it's gotten really, really super easy with the duplicate row filter. This is a feature of the duplicate row filter that I had either not known about or forgotten. The two are essentially the same. And I thank Steve for pointing this out to me, or reminding me, whichever one is true. Let's look at the duplicate row filter. The first thing I do is I pick the row or the column that I want to use to identify duplicates. And in this case, that's PDB ID. So I want in the output table, each PDB ID should appear only once. And then on the advanced tab, I say I want to remove duplicate rows. That's the default. But the thing that's not the default is I say I want to select the row that contains the maximum of ligand molecular weight. So what that will do is go through the table and find each of the rows for all of the rows that have the same PDB ID. It'll take the one that has the largest molecular weight. And when it does that, it retains the same row order in the output table. It's really cool. This used to be complicated to do, and now it's super, super easy. It's great functionality in the duplicate row filter. So now I'm back down to 294 structures. I started with 294 PDB structures. That got expanded to 1510 by this custom report. And with the duplicate row filter, I'm down to 294. And for each PDB structure, I have only the one with the largest molecular weight. Now, remember when we looked at the table before, some of those don't actually have a ligand in it. So I want to remove those, and I do that with a row filter. So I'm going to look at the ligand molecular weight column and exclude any row where that value is missing. So we can recognize that by looking at the output table from the duplicate row filter. You can see that some of these, for some of the combinations of a PDB and a chain ID, there's no ligand ID, it's a missing value, or the molecular weight is also missing. So we want to remove any row where that's true, so that's any structure that doesn't have a ligand. By the time we do that, we go down from 294 to 265, and now we have the most recent structures from the PDB that contain a ligand, and for each of those, we have only the largest ligand. Now, just to make the rest of this go faster, I filtered that down to 200. That's in case you run this and the most recent structures ends up returning a rather large number. It then takes a very long time to get all the results. Next step is to download from the PDB all of the PDB data. itself, so the PDB for each of those PDB IDs. You can see what I now have is that node has added in a new column to the data set. I still have 200 rows, and for each of the PDB IDs, I have the actual PDB data, so the PDB file. Next step, I want to get the 3D structures of the ligands, because in the view at the end, well, actually, let me show you the view. I should have done this at the beginning, I apologize. Let me show you where we're going to, so you can understand what this next step is. So I'm going to open the view on this component that's at the end. And what we have here is a 3D molecule viewer. This is 3D Mol.js from David Coase at the University of Pittsburgh. And I'm going to tell it to listen to the selection events. Down at the bottom, I have a table of my structure. So I have the ligand drawn, and then some information about it. And you can see some of these structures, even though I said ligand only, I'm getting salt information, or sulfates are not really interesting. But let me just sort the table by molecular weight so we can get the things that look more like actual ligands. We can select this one. So I'll select the ligand. Go back up, and now you can see in 3D Mol.js, this is the 3D structure of the ligand as it was found in that protein structure. If I want to, I can also show the protein itself. So by switching the column, so here's the full structure of the PDB. Unfortunately, none of us know 3D Mol.js well enough to figure out how to change the view in this. So it shows the protein with like the nice cartoon structure with the ribbons. And so ideally, I could have some way where I show the ribbons to see the alpha helices and beta sheets, and can also zoom in on the ligand. We don't know 3D Mol.js well enough. Hopefully we can figure that out sometime in a reasonably near future. But in the meantime, you can still, this is not useless as it is. If anybody knows how to do that with 3D Mol.js, please get in touch, or I'll show you how we built this. You can even do it yourself. Anyway, that's what we want to get. So we have the PDB information already. Now I need the ligand information. And it turns out the PDB makes a web service available to do this. I've never found a documentation for the web service. I just figured out how to use it. So that's what we're doing here. So I do a little bit of string manipulation to construct a URL for the web service. I use KNIME's web service nodes to hit that web service and get the results. And in the end, what I end up with is a new column in my table that has the SDF data for that particular ligand. You can see I don't get it for every structure, unfortunately. Okay, and then once we have that, then I have everything I need to construct the view that I showed you, right? So I have the SDF for the ligand structure, I have the PDB so I can show the full protein, and I have the information about the PDB ID, the ligand ID, et cetera. Let's see how to construct that view. Again, this is a component which Elise showed you already. So I'm going to control double click to go inside that. If you're on a Mac, that's command double click. I have two views here. The first is the table view. That's what was down at the bottom of that. Remember, it showed the pictures of the molecules. Well, we can see what it shows. So let me open the view. It's showing it's going to have the pictures of the molecules and then some of the other information. So we have the ligand ID, the PDB ID, the chain ID, and the ligand molecular weight, as well as the formula. Then, because we don't have a 3D molecule viewer built into KNIME, we have this generic JavaScript view that's using 3D Mol.js, as I mentioned, to do the actual visualization. KNIME's generic JavaScript view is super useful if there's a JavaScript library that you would like to use inside of KNIME to do something that we don't have a node for already. I'm not going to get into the details of this, and it's not because we don't have time. I'll be upfront, I don't really know how this works. I'm not a JavaScript person. Alex at KNIME did the work to build this. It's really, really useful. But what this basically does, I'll open it so we can all stare at the code. What Alex built here is there's a bunch of code that works with with 3D Mol.js, and integrates with the selection mechanism that KNIME's composite views provide, so that when you select a molecule or when you select a row, the information about that row is sent to the viewer. And yeah. Okay, so the other pieces in this component we've seen already. So Elise showed you some of this. There's the RDKit from molecule node, and then the rendered image, which takes that RDKit molecule and turns it into an SVG so that we can show it in the table. I have to apologize that you have to do this because it's kind of ugly and it's not really very particularly user-friendly. I hope that at one of the next few releases of KNIME, we get it so that you don't have to do this anymore, so that it will automatically put the molecule pictures in for you. And again, that's not going to be in the next release, but hopefully we can get it in at some point. I also had a column resorter, and that's just I wanted to have the pictures of the molecules at the front instead of at the end, because I like to have molecule pictures early. And then for the generic JavaScript view, I didn't want to confuse things with the generic JavaScript view. So I have a column filter and just limit the number of nodes that go, or the number of columns that go into that. So that node is really only getting the 2 columns that we care about, the ligand and the PDB. Okay, so that was the component. I also wanted to have this be in the proper order. So with the layout editor, I told it to put the JavaScript, the generic JavaScript view up top, and then the table view below that, so that we can see the 3D structure takes priority. It's the first thing we see. And again, we can just go back and look at that because it's nice. I'm just so happy about this because we've not really had 3D molecules in KNIME before, except for with commercial nodes. So it's really nice to be able to do this with the purely open source nodes. And 3D-Mold.js is a really nice tool. So it does a nice job of rendering things. We don't see it here because we're not taking advantage of any of the super advanced functionality. Let's go through and we can look at a couple more molecules. One thing that is worth pointing out is the table allows you to select multiple rows. And if you do that, this will show you multiple things, but that's not always particularly useful because the molecules are not necessarily in the same reference frame. I happen to get lucky there that these are reasonably close to each other, but it's pretty easy to end up with molecules spread out all over the place, as you can see here. So if we wanted to be able to make it easier to see all of them, to see multiple molecules at the same time, obviously we'd have to do something like aligning active sites to each other or just centering all the molecules. These are all refinements that we can do. I'm running out of time, so let me stop. I want to emphasize, so you have this workflow. We will eventually do a component for the 3D molecule viewer. We want to do a little bit more testing around that and some verification, and then that will show up on the verified components list along with all of the other verified components. At that, I'll stop. Let's see if there are any questions out there. Elise, has anything come up?
We have 3 more chemical questions and 2 open that I think I will cover in the wrap-up.
Okay.
So if you define variable R groups in Marvin Sketch, will the RDKit reaction node recognize the reactants?
No, I think we covered that one already.
That one?
Yeah.
Then I will go and hide it. And good one, since there is a unify products checkbox in the reaction nodes, why do you need to filter for duplicates?
So that's a really good question. We could have just done Uniquify products and then it actually, I'm trying to remember what that does. It's been a long time since we worked on that node. It may be that Uniquify products only works for one set of reactants at a time. So I mentioned that if you have symmetry, one set of reactants can produce multiple output rows, and that Uniquify products works at that level. It may be across the whole table. To be honest, I don't remember. I'm just I compulsively throw that duplicate remover thing or duplicate removal in there. And I don't even really think about other options, but that's a really good question.
It is, and it is needed. So I just tried it out. If I click this unify, it doesn't give me the same output as my duplicate row filter.
Yeah, then it's doing what I described. So it's doing, if you have multiple mappings of a reactant onto the reaction, so you get multiple rows, if those produce the same degenerate results, it will remove them.
Right. And just another one. Yeah, we have the minute. What is the reason why I canonicalize again before the duplicate row filter? This was in my workflow. It's just that whatever comes out of the two-component reaction just is not canonicalized yet. So I did that before, but once the reaction is running over all the molecules and the structures, it's not. So I go and have to do that one again. This is the reason why I had that note.
So I see there's also a question about training for chemistry and KNIME. So
yes, this is where I would go back and
okay, very good. Thank you.
Have the screen and pull up slides again. So I wanted to point out our life science landing page. So if you want to find out more what KNIME can do for you in the life science area, I would strongly recommend you go and check out that site. And also some additional resources. So I was mentioning the hub already in the beginning, but if you want to you need more information, you want to have more information, we have plenty of other resources. So we're having a learning hub. This is the hub that I mentioned. We're having a row of a number of books available to learn KNIME, and I will also give you a code for these in just a second. I was also pointing out to the forum. This is again where I would question you. If we didn't cover your question today, go and post it there. We're having a really active community. We're checking this out ourselves regularly. So whatever doesn't get covered by our other communities, so not KNIMers, and there are really a lot, eventually ends up with us, and we will make sure that this is getting answered. We're also having a lot of documentation, frequently asked questions, logs available at docs.knime. And also, especially if you're starting with KNIME, I can really highly recommend go and check out our YouTube channel. We're having really nice, like a few minutes videos for single tasks that will support you getting into it. Now coming to the questions, how to get an expert. Amongst KNIME events, we're regularly publishing all the trainings and courses that we're giving. And we had a dedicated chemical data course, or we're still having it. It's just a bit unfortunate that we had this running twice recently. So I think the last one was just in October. I can't tell you exactly when the next one's gonna be happening, but please go and check by the events page. And if it's gonna run again, you can go and sign up there. Then maybe 1 minute, Greg was mentioning the verified components. So these components that we showed both in our workflows, these are a really powerful tool, and we also noticed that ourselves at KNIME. So we're building them ourselves from KNIME employees, and they're really verified. We're also having a page for that, and we're also right now working on this 3D visualization component. This one's gonna eventually also show up at this verified components page. And with that, I would be still in time, perfectly at the end. Thank you all for joining. And I hope you found that useful, and hopefully see you again at one of our trainings.
Thank you, everyone.